Yeah, hello. Well, Tim introduced me already, so I just start with the next slide. Why do we do that? First of all, I talk about localization before I come into the driving itself, which we also classify as a part of the navigation. And localization is, as Tim mentioned in his lecture yesterday, especially important for to communicate poses of MPSs between the robots. So you need to have a common frame, which we call map, where you can define positions in, and then other robots know about this position as well. So that will be the first part, and then the longer part of the presentation will be the actual driving onto the RoboCup field and how we do it, so that we can drive without colliding with MPSs, walls, or other robots. So first I start to talk about the frames that are important for this. The first important thing is the odometry frame, which is called Odom, and the baselink frame. And this frame, or this connection, is published by the motor. That's quite common doing in robotics to have it like that. The Odom frame then usually starts where the robot were booted. Yes?
Coordinate frame, right?
Excuse me?
You might not recall frame. Coordinate frame.
Coordinate frame, yeah.
Just so you all know it's a coordinate frame. So when you're wondering what the frame is.
Hier oder was? Okay. Ist besser? Okay. Was denn?
Ja, wenn es still ist. Also wenn du dich nicht bewegst, deswegen.
Okay. Besser?
Ja.
Okay. Auch wenn ich mich bewege jetzt? Okay? Okay. So the odometry frame is typically calculated by sensors on the robot. In the case of the Robotino, it's wheel encoders and the IMU. The Robotino 3 has a built-in IMU, but we also use IMU from the previous version, which is quite better. So we're using both to calculate the odometry. Which has the positive side that this is a continuous frame, so you don't have jumps in it. It's continuously integrated by the sensors, but also is drifting over the time. So you always have the error of the sensors, which are over the time become larger and larger. And this is why you also typically have a map frame, which is then published by your localization software. And in the bottom, you also see a link on ROS, where they describe the frames and, well, what they're typically doing and what they're for. My talk will be ordered like that. So navigation and why it's about, we already did. So now we're going to go to the localization. Then we talk about the global planner, then an automatically generation of it, which will become clear during the talk why that is necessary. Then the local planner, and then I finish with how we actually use that. So the localization comes now. We're using RCL for localization, which stands for Adaptive Monte Carlo Localization, which is a particle filter, and so it has a lot of particles, and then tries to, for each particle, assumes that if that would be the pose, how possible is it that this is a pose by verifying the laser data against the map. So here on the right side, for example, we have these black outlines, which are the map. The bright part, which you can just see a little bit, which is the inside of the map, or the known area, which is thought to be free. And then gray is typically the unknown part of that. And the red part is the hypothesis of the Monte Carlo localization where you believe where your robot is. So at the beginning you don't have any idea where your robot is, and then when you start to drive, you also start to move your hypothesis in the direction of your driven path. So if you drive 1 meter forward, they all would move 1 meter forward, and then if you have something like here facing this direction, you would then be here. So then the more you drive and the more you validate your lasers, the more sure you're going to be where your actual localization is. So just a few. For example, you drove a little bit, maybe conquered the corner, then you just can be somewhere behind the corner, for example at these positions. Further, you maybe drove past here, and you conquered this feature, then you know you're here, and then if you drive further, you just become more clear. You never be in just one specific position, you always have a few samples there. So that you can also, well, if you have an error in everything, you can then get fixed again to a correct position. Well, yeah, that's how it is. And to go back to our previous figure, where we had these 3 frames, what we're doing here is well, the localization estimates the map against the robot position, but what's actually published is just a map to the odometry. Yes. So then, what is a map in the RoboCup for us? The map that we used in China is this, which just outlining the robot insertion areas and the outlining of the walls they were piled up in China. We're using a hand-drawn map using GIMP, which just image manipulation software, and we're using 1 pixel as 5 centimeters. You also could use SLAM algorithms or like hectoslam or gmapping. But you need to keep in mind that, if robots might maybe do collide with FESs and move them during the game, they might not necessarily be put back. So if you include MPSs in this, then you might have wrong features in your map during the game. It's uncommon, but it can happen. So, the next part will be about the path planning. So the typical way of path planning in robotics is that you have a map base or global planner, which is, as the name said, based on the map. So a sensor-based planner or local planner, which is based on sensors, and then the realization of the driving commands by the motor. In the Fawkes robotic framework, this is called the global planner called NavGraph, the local planner Collie, and the motor is called Robotino. Okay, now we start to talk about the NavGraph. The NavGraph that we're using is a topological graph. The idea is that you have your map, and then you have a graph sitting on top of the map. And with this graph, you have connections that are obstacle-free by the map. So if you would have, if just your robot would be in this room, you could follow all the lines on your graph and would not collide with anything. So that you have an abstract visualization of your environment. And then if you would, for example, want to drive from this point to this point, you would do search on your graph. You would get this as the shortest path that's obstacle-free by the map, and then you would try to follow them. That is how it looks like in the Fawkes robotic framework, NavGraph. It's well, that's a NavGraph that we used 2014, where we had these fixed layout of the machines. So each of these points were one of the machines, and you had a very fixed grid, and This were configured using a YAML file where we had a node list and an edge list that then connected these. And nodes then have an X and Y coordinate, and they're connected by edges. Furthermore, nodes do have properties. The most common property is the orientation. All the nodes on the what we call highways, or just there to drive in between the machines, typically don't have orientation. But the nodes facing towards the machine do normally face in the direction of the machine. That furthermore got extended by thresholds. So, for example, when you later on drive on your graph, you have thresholds how far your robot needs to come to one node so that it goes to the next node. I will describe that in the next few slides in more detail. But we then extended it even more, so we now have properties that are not directly used for the navigation, but for example, we store properties of the machines in these nodes. So for example, the signal light that you just saw, where for each machine the signal light is roughly depending on the laser lines, is stored there, or where the conveyor belt is as an offset from the tag on this machine is also stored there, or more generalized, which tag is on the input and output side of this machine. So that are information that we store in this in these properties. Furthermore, that's the path. I have that on most of my slides coming now about the plugin I'm talking about, and this is the path where where the nav graph that we're currently using is located. So that is how the nav graph for us looks at the moment. If you drive on it now, you first of all you have your robot location somewhere here, for example, and you want to drive to here. Then you define that as your target, and then the nav graph starts to calculate a plan to follow, to drive over this path. That is done using the R star algorithm, which is an efficient algorithm to calculate on a graph-based environment. You typically need an estimation how far the nodes are apart from each other. In the navigation, that's quite easy to do by having the Euclidean distance between the nodes. And then your extra cost, which is most of the case also the Euclidean distance in the graph. And then you get these paths. What you furthermore see here are the thresholds I talked about. So that is this, at the moment the robot wants to try to reach this point. And this point has this threshold as this threshold that if that's reached by the robot, the next node is tried to be the target for the local planner. So that also means at corners that if this threshold for this node is reached, the robot tries to drive to here. So the robot actually will not drive here, follow directly very closely to that, and then very close to here, but more likely drives something like that. Of course, if you make the threshold smaller, you drive it more closely. So, I now have a few slides where you can see when it's jumping. So now it reached the threshold, and that is now the target for it. This threshold it tries to drive to the next one, and so on. And you see then that the local path planner is avoiding these obstacles that you can see here with white dots, which are the laser of the robot, until it reaches this last part. And here you see a way smaller threshold for its target. That's because the last node and this is target threshold is typically smaller than the threshold on the nodes that are in between the paths. So and then here it reaches target. So I quickly go back. As you, for example, saw here, this is a NAV graph, what we call our basic NAV graph. And if you're familiar with the setup of the or the layout of the playing field, you see that these nodes are actually on the borders of the zones where the MPS machines can be put into. So these zones are always 1.5 meter in the upward direction with the Y direction, and 2 meters in the X direction. So this is always one zone where an MPS can stand anywhere inside. And we use this as a good first idea where it's unlikely that an MPS is standing, so it's unlikely that we have an obstacle in between. But for example, here you can see that the MPS is very close to the border. So that's obstructing the paths. That's obstructing the path that the robot wants to take. So as I described earlier, with the NAV graph, we want to try have a path that is obstacle-free by static obstacles, which would be these MPSs. So what we do now is then, if we during the exploration find any MPSs, we then include them in the graph, and that's what I come to now. That which is automatic generation of the graph. So as I said, that is the basis, and what we use during the exploration, we drive around and try to find the MPSs. And if an MPS is found, then it's added. We as an agent, which then calls a plugin which called NavGraph Generator MPS, which generates for these detected MPS the input and output points, and also the points of the actual machine, where the properties, for example, that I talked about are stored in. And then these plugin calls the NavGraph Generator, which then generalize in a generalized way add these points to the NAV graph and calculates the new graph. And the new graph is calculated using a Voronoi diagram. So I now just want to quickly show how it looks like. This is when, for example, the first MPS, which is in this case the delivery machine, is found. You see here an unconnected node of the delivery, and then the two input nodes, the input node and the output node of this machine. And yeah, that's the first MPS added. The second MPS was found here, and the input node and output node here. So you have this, and so on. So that would be the third MPS, the fourth, the fifth, and the sixth. And after we added all or found all 6 MPSs and the game starts, we then know, because it's defined in the rules, that MPSs for the opponent team are mirrored on the game field, so that we mirror the found positions of our MPSs as well, so that we then get this mirrored graph, where each position of where we found an MPS is just mirrored on the other side of the game field, or playing field. And then the next step, where I don't have a picture for, is then the basic graph that we used at the beginning removed. So we just have the generated path to drive on during the game, which is then hopefully, if we don't do any errors, obstacle-free by static obstacles. So we just need to care about moving robots of ourselves or the other team or referees, or as in China, security people running over the field. So that's a global planner, or the map-based planner. And now we're going to go to the local planner, or sensor-based planner, which is called Collie, where we then describe, if we drive on this NAV graph, how we avoid dynamic obstacles, or obstacles that still appear in them. So first of all, how it looks for the robot. Well, the robot is here, and we're using for this path planner, we're using the laser data to calculate obstacles. and a grid. The grid you can't see here. You can just imagine a grid around the robot, which 5 centimeter distance, where the obstacles are injured. So you have these laser data and then the obstacles, and this would look like that then. And what you typically do is, for each laser data, you extend your laser data by the robot size, so that you then, in your comparison, you just need to compare, can think about the robot as a dot, and your obstacles are extended by the size of the robot, so that you just need to compare a dot against a plane. So, how we get there, and what do we do during that? That is the workflow of our local planner, that which is called with 10 hertz periodically, and I think one that's very special about this planner is that it's mostly stateless. So if it plans a pass during one step, and then it's called after 0.1 seconds again, it calculates a totally new pass. And it always follows these 4 steps to firstly create an obstacle map. The result is what you just saw on the slide before. It then plans on this obstacle map, and then the last two you will see when I get to them. They're very specific for this class planner. So the obstacle map is firstly created by the laser beams, and then you increase the laser beams by the size of the robot, for example that. And then each cell on your grid, which is occupied by these areas, is then interpreted as an occupied cell, which you should avoid when you're driving. That's a robot, and that is the goal you want to fully find. So that's how you create the obstacle map at the first step. Here you see the result of the obstacle map. And then on this grid with the obstacles put in, you calculate your paths. For that, we use the A-star algorithm again. This time with the Manhattan distance as a distance between this node. So each cell is a node, as before in the graphs that we used to calculate the algorithm in. Well, as I said, we use the Manhattan distance. The Manhattan distance is the distance between two fields. Which also results that this, for example, one valid plan. Also valid plan with the same cost would be directly go to here, then straight up, and then to here. It would be another plan that would be valid with the same cost as this. Good. What we then do in the second step of the planning is we try to find on our plan that we had the next point on the plan, which is which you can directly reach. We do that by raycasting from the position on the plan to the robot position. And if you see here, you would then if you would reach this point and would try to raycast to the robot, you would need to go through the obstacle. So that's where W is the next point, which we then, as on the plan, want to fully want to reach as the next step. So we then go to the drive mode, and in the drive mode, we then try to find with the characteristics of our robot a way to drive to this position without colliding to the obstacle. This graphic is from a robot which differential drive, so they have these curves they want to try to fully to reach that. On the Robotino, we have implemented a new drive mode with just very simpler following directly this line to try to fullify this straight by during the driving slowly turning towards the target. And then the last step, the drive localization, is simply a linear change of the velocity. It's implemented in a dynamic way. We also had once in other ways to increase or decrease the velocities. So that is the same situation as before, where we start here with our robot and then want to fullify to get to here. What you now see is, as before, you had these shapes here, and now you also see the obstacles as it's seen by the robot. I just talked about the red obstacles before. We also have yellow and green parts of it, which are then just have a slightly higher cost than unoccupied cells, while the red part has a way higher cost than unoccupied cells. And furthermore, you see the blue path, which is the path that's calculated by the planning algorithm to the next goal. And that is the video where you can see the whole drive. And you see as soon as the threshold is reached, it jumps to the next part and then tries to drive to there. So, now the next, I want to just say a few words to the Robotino plugin, which controls the motor. The Robotino plugin is, well, it gets a transport message, which is gets a velocity in x and in y direction, and furthermore omega, also the velocity in the rotational velocity. And furthermore, important for us is the odometry, because the odometry is published by this plugin. And to communicate with the Robotino, it uses the Open Robotino API. And furthermore, it also has published a Robotino sensor interface, which well, gives you information about the sensors on the Robotino platform, the AD sensors, where we sometimes connect light signals to, or the infrared sensors that are wired around it, and all these stuff. It also published the IMU of the Robotino 3, which is intern, and it gives a gripper interface, but not for the gripper that we are using. That is a gripper interface for the gripper that comes with the Robotino. So if you use that and connect it to your robot and want to use it, then you need to use the Robotino plugin and our software for that. And now I want to show you how we are going to actually use this path planning part. As you see in the figure on top of it, the graphic from the beginning. Now with these dots in between, which should show the interfaces that are part of the path planning. So on the left-hand side, you have the path plan interface, which is a navigation interface, and which you can use to control the nav graph. And you can send to that a place go-to message, which gets in place on the nav graph. And then the nav graph tries to fullify this plan as I just described, and uses the interfaces to control the colony, which then uses this interface to control the Robotino, and so on. So that interface is in the map frame, so you define a the map frame coordinate, which is try to fullify in the way I described. Then you have the navigator interface, which is the collie. So if you send a message to here, you don't use the nav graph to plan it. Then you directly try to fullify this plan with the collie and then with the Robotino. This is in a base link frame. So if you and get a Cartesian go-to message typically with x, y, and theta. And this means if you send it, for example, x equals 1 as a message, then the robot drives 1 meter forward. That means that because it's in the baseline frame. If you would do a similar message in the map frame, for example, it would drive 1 meter to the side from the viewpoint of the map. And then at last, you can also use the Robotino interface. But you need to keep in mind, if you do that, you don't have any collision avoidance. And there you send a transport message, so you send the velocity x, or the velocity of y, and omega, which is also in the baseline frame. But as different before, you don't send coordinates, you send velocities. And in the last handle section, at the end, Victor also talked about skills. In 2 days, you have a detailed description about what skills are. Here I just list the skills that we are using for path planning, so you can later in the simulation play around with them and see what happens. To use the path planner, we first use the rel goto and goto. The rel goto stands for relatively goto, and it uses the collie, so the path planner, the nav graph is not used in it. So just use the collie and then Robotino. And well, rel goto is relatively, so use the base link. So if you define x equals 1, for example, your robot would drive 1 meter forward. The goto uses also just the collie, but is in the map frame. So if you there would define x equals 1, you would not drive 1 meter forward, but you would drive to the coordinate x equals where x equals 1, which is actually in a wall, so better say y equals 1, that is in the center of the map and then 1 meter inside the playing field. And the last skill that uses the path planner is the PV goto, which historically stands for path plan goto, which uses a nav graph as well, and that's the most common skill that we are using during the game. And they define place on the nav graph to drive to. Furthermore, we also use the motor move skill, where we don't use any collision avoidance to adjust us very precisely in front of machines, for example. But you should keep in mind that here you don't have any collision avoidance and just should drive short passes to adjust any position. And you also should verify, you should be sure that you're just driving short passes, because we had that in the past where one of these skills failed, and then these were called, so we were trying to move through the whole map without collision avoidance, and we're driving into stuff. As a summary, I started to talk about the localization, why it's important, and what we are using to localize ourselves within the map. I then talked about the global nav graph as a global planner, which is called nav graph in the Fawkes robotic framework, which is based on topological graph, and then since this here is also generated automatically, so we can append it to the changing playing field, and then about the local path planner. And now, as a hands-on, we prepared the setup that we also can fully find in the other hall for you, where you firstly need to change the map to an obstacle that's put in there. For that you should use GIMP, and remember that 1 pixel is equal to 5 centimeter. We also prepared a simulation, so you can do it here on your laptops using the simulation. Well, that's the first step. If you're done with that, you need to create the nav graph, and it's 3 MPSs in this example, so you need to create the MPSs point with the properties that are described, which you can copy from our previous nav graph, but the rest needs to be done totally new. And if that's done, you need to drive on the nav graph with the skills and just get used to it, what happens if you call which skill. And that is how I finish my talk. So thank you for your attention.